This video is going to look at what's called the second derivative test. And I want to warn you that I know that we looked at using the second derivative in a previous video where we were finding the concavity, whether the graph was concave up or concave down. Now, that is not the second derivative test. That is just a test to find concavity using the second derivative. So that's just a way that we can find the concavity using the second derivative. What we refer to as the second derivative test is another way to identify our relative max and relative minimum points. And if you recall, we looked at a way using the first derivative to find our relative max and relative min, and we said that if your function was decreasing and then all of a sudden it changed to increasing, we would have a relative minimum, and if our graph went from increasing to decreasing, it would have a relative maximum. Well, the second derivative test is a shortcut as long as the second derivative exists and as long as the second derivative does not equal to 0. And what that tells us is if we locate f prime of c where that's equal to 0, and if you recall, this is where we were finding our critical number, okay, or your critical points. So if we find our critical number, then we know that's going to be a point where our graph could change directions. Well, if we plug that into the second derivative at that critical number, and if it's greater than 0, or which means it's positive, that means we would have a concavity would be concave up. Well, if at this critical point it's concave up, clearly we would have a relative minimum. And similarly over here, if we take our derivative, set it equal to 0, and once again, this allows us to find our critical number c. And if we take that critical number and plug it into the second derivative, and if it's negative, that's going to tell us that it is concave down. Well, if the graph is concave down, then that means our point, our critical number, must be a relative max. So again, the second derivative test is a shortcut way of identifying your relative min and relative max. So let's apply that to this example here. F of x equals x squared plus 3x minus 8. We want to use the second derivative test to identify our relative max and relative min. So first of all, we're going to take the first derivative, and we would have 2x plus 3. And we need to identify the critical point, so we're going to set this equal to 0. So 2x equals negative 3, so x equals a negative 3/2. This is going to be our critical number. So now we must find the second derivative. And if you notice up here, if we take the second derivative of 2x, that's just simply going to be 2x, simply going to be 2. And now we need to evaluate the second derivative at the negative 3/2. Now, if you notice, there's no x up here in the second derivative. All we have is a 2. Well, that means it's a constant. So it doesn't matter what our value is. If we plug a negative 3/2 in, it's always going to be 2. Well, we know that this is a positive number, so therefore that tells us our graph is going to be concave up. And if our graph is concave up at negative 3/2, then that tells us that the negative 3/2 here, we would have a relative minimum. Okay, so you got to be careful. It's positive, which means it's concave up, and if it's concave up, we have a relative minimum. So that would be at negative 3/2. Now, how do we find our y value? Well, if we find the y value, remember this is to the original function, so we need to plug the negative 3/2 back into the original function, and if you do so, you will end up with a negative 10.25. So that's going to be our relative minimum point. Now, you won't always have your second derivative just equal to a constant. For example, if we took the second derivative and we had something like 2x plus 4, then you would plug 2 in and you would get you'd plug the negative 3/2 in, 2 times negative 3/2 plus 4, and you would determine if that's positive or negative. Now in this example, you notice that our second derivative is equal to 2. It's constant. So that means that our graph is always concave up. So that means there's no point of inflection. The concavity is not going to change. And we probably could have determined that if we looked at the function closely. X squared plus 3x minus 8 we know is going to be a parabola that opens up, and we know it would have a relative minimum point because it's opening upwards. And if you notice the concavity, it is always concave up. All right, if we look at one more example here, x cubed minus 9x squared plus 27x. Again, we want to use the second derivative, if possible, the second derivative test, that is, to find relative max and min. So we're going to start out by finding the first derivative, which would be 3x squared minus 18x squared, minus 18x plus 27. And once again, we need to find the critical points, your critical numbers. So we're going to set this equal to 0 and solve for x. And we have a 3, a 18, and a 27. So to make it easier, I'm going to divide everything by 3. So we would end up with x squared minus 6x plus 9. So now that's going to make it easier to factor. You don't necessarily have to do that, but now when we go to factor, it's going to be a lot easier. So we have x times x, and it looks like 3 times 3 is our 9, and both are negative. So if we set each factor equal to 0, we're going to get x equals 3. So this here is our critical number. So now we need to calculate the second derivative, because that's going to give us our concavity. So the second derivative here would simply be 2 times 3 would be 6x minus 18. So if we evaluate the second derivative at our critical number, which is 3, notice here we're going to get 6 times 3, which is 18 minus 18. We end up with 0. Well, this is one of those conditions where, because it's equal to 0, our test fails. So that simply means we can't use the second derivative test. We must use the first derivative. So simply that means we're going to have to use what we did earlier in the previous video, and that means we need to find our critical points, which we already have, is 3, and we would use our test intervals, and that means we would look from negative infinity to 3, from 3 to infinity, and pick a test point. Well, negative infinity to 3, I would pick 0, and then from 3 to infinity, use 4. And then we need to evaluate those at the first derivative. So plug 0 into the first derivative. And clearly, if we look at the first derivative up here, if we plug 0 in for x, we're going to end up with a positive answer. And if we plug in 4, you would also end up with a positive number. So what can we conclude based on this? Well, if it's positive, that means our graph is increasing, and it's still increasing from 3 to infinity. So what does that tell us? Well, if it's continuously increasing from a negative infinity to positive infinity, then there's no relative extrema. So you will notice that the second derivative test now is just simply another way that we can identify relative minimum and relative maximum as long as our second derivative exists. Because what the second derivative, remember, tells us is the concavity. And if we know the concavity at our critical number, then we can determine whether it's a relative max or relative min. But as our second example shows, if we get 0 or the second derivative does not exist, we have to use the first derivative test.